Far beyond the familiar comfort of our solar system, in the dim expanse between stars, a whisper has reached us. Not a sound, for sound cannot travel through the vacuum of space, but a flicker of light, a telltale shadow, a subtle curve in data that speaks louder than thunder. Astronomers, peering through the colossal lenses of Earth's most advanced observatories and the cold, sensitive eyes of space telescopes, have seen something extraordinary. A world orbiting a distant star that carries the unmistakable fingerprints of habitability. Numbers, calculations, and simulations converge on a single conclusion, so bold it shakes the foundation of our cosmic solitude. There is a 98% chance that this planet harbors life. Imagine the scene in the control rooms of observatories across the globe. Banks of monitors glowing in the darkness, the silence broken only by the rhythmic tapping of keyboards and the soft hum of servers. Data streams in. Light that has traveled for hundreds of years suddenly finds itself translated into graphs, curves, and probabilities. On one of these screens, a probability index climbs higher and higher, creeping past the thresholds of speculation, breaching the walls of skepticism, and finally settling near certainty. The astronomers know that science rarely deals in absolutes. It lives in the gray areas of doubt, where certainty is a fleeting thing. Yet here was a number, 98%, a number so close to truth it almost feels like revelation. But how do we, perched on our small, fragile Earth, dare to make such a claim about a world so far away that no human eye will ever see it directly? The answer lies in the extraordinary tools humanity has built. Instruments capable of peeling back the layers of the cosmos like the pages of a book. One of the most revolutionary among them is the transit method. When a planet passes in front of its star, as seen from our vantage point, it dims the star's light by a tiny fraction. To the naked eye, this dimming would be imperceptible, but to a telescope fine-tuned to the rhythms of starlight, it is as clear as a heartbeat on an electrocardiogram. With each orbit, the planet draws a shadow, leaving behind a signature from which astronomers can calculate its size, its orbital distance, even the potential composition of its atmosphere. And this is where the story deepens, for in the faint afterglow of that star's light, filtered through the thin veil of the planet's atmosphere, scientists detect the presence of molecules. Oxygen, methane, water vapor, ingredients that, in combination, form the alchemy of life. Not proof, no, but tantalizing hints, like the faint scent of smoke carried on the wind, suggesting a fire unseen beyond the horizon. On Earth, such a cocktail of gases does not remain stable without the intervention of biology. Life consumes and produces them in a perpetual cycle. The implication is staggering. If these signatures are real, then something is breathing beneath that alien sky. The announcement spreads quickly, carried on the wings of media headlines and whispered in the halls of universities. A planet with a 98% chance of life. For the first time in human history, the numbers point not just to possibility, but to near certainty. The reaction is as diverse as humanity itself. Some are overwhelmed with awe, others with fear. For centuries, we have looked at the night sky and wondered if we are alone. Now, for the first time, science suggests an answer that lies not in philosophy or faith, but in data. And yet the question deepens rather than resolves. What kind of life? Bacterial mats clinging to rocks beneath an alien ocean? Vast forests of strange flora swaying under a distant sun? Or something more? Beings that, like us, look up at their sky and wonder if they are alone. To appreciate the magnitude of this discovery, one must step back and consider the vastness of the search. Our galaxy alone holds hundreds of billions of stars, each potentially surrounded by planets. The Kepler mission, launched in 2009, revealed that planets are not rare jewels, but common companions to stars, far more numerous than we dared to imagine. Among these billions, Earth-like worlds, those rocky planets sitting in the temperate zone where liquid water can flow, are not the exception, but the rule. Statistically, the Milky Way should be teeming with places like Earth. And yet, until now, we had no confirmation that life might actually be present on any of them. For decades, the silence of the universe mocked our expectations. The famous paradox posed by Enrico Fermi, "If life is common, where is everyone?" loomed over every discovery. And then came this world. Orbiting a sun-like star at just the right distance, cloaked in an atmosphere rich with the signs of chemistry we know and recognize. Its discovery was not the result of chance, but of years of meticulous observation. Teams of scientists across continents comparing notes, running models, ruling out contamination or error. At every step, the probability sharpened until it reached that astonishing figure, 98%. Not certainty, but as close as science can come without setting foot on alien soil. Picture it now, this distant planet. Bathed in the pale light of its sun, it circles endlessly, oblivious to the excitement it has stirred on a small blue world light years away. Perhaps its skies are painted in colors unfamiliar to human eyes. Perhaps oceans roll beneath clouds of ammonia or methane. Or perhaps water glitters there, catching the light in waves just as it does here on Earth. If life has indeed taken root, then every second of every day, unseen by us, countless organisms live and die, evolve and adapt, carrying forward a chain of existence that began millions, maybe billions of years ago. A parallel story of life unfolding in silence. The tension lies here, in the gap between probability and proof. For while instruments can tell us much, they cannot yet carry us there. Even the most advanced telescopes cannot reveal the full truth of what thrives beneath that sky. We are left with inference, with a number, with 98%. And that number, for now, is both a promise and a challenge. A promise that life is not unique to Earth, and a challenge to build the means to confirm it. In the years to come, missions will be planned with this goal in mind. Telescopes designed not just to find planets, but to study their atmospheres in exquisite detail. Concepts like the LUVOR and HABEX space telescopes, or star shades that can block the blinding glare of a host star, allowing us to see the faint glimmer of a planet beside it. Each innovation brings us closer to the moment when for the first time we might actually glimpse an alien world not as a dot of light, but as a place, clouds, continents, oceans, proof beyond probability. But even before that moment arrives, the psychological shift is already underway. For thousands of years, we have lived with the possibility of life beyond Earth as speculation, myth, or hope. Now, for the first time, it stands before us as almost certain. We are not isolated miracles adrift in a sterile cosmos. We are part of something larger, a living galaxy, perhaps even a living universe. And as we let this realization sink in, one question rises inexorably. If life is out there, what does it mean for us? Long before the numbers appeared on computer screens and the probability of extraterrestrial life solidified into a staggering 98%, humanity's search had always been more of a dream than a calculation. For millennia, when our ancestors gazed into the night sky, they saw not data, but stories. Constellations became gods, heroes, and creatures, woven into myths to explain the vast unknown. The Greeks imagined Zeus placing figures among the stars. The Egyptians aligned pyramids with Orion's belt, believing it a cosmic guide. The night sky was a canvas, and on it, humanity projected its fears, hopes, and beliefs. Yet hidden behind those myths was always the deeper question: are we alone? That question began to take its first steps toward science in the Renaissance, when Galileo Galilei raised a crude telescope to the heavens and shattered the old world view. The moon was not a perfect, divine orb, but scarred with mountains and valleys. Jupiter had its own miniature system of moons, worlds circling a world, echoing the Earth's relationship with the Sun. Suddenly, the cosmos seemed vast and complex, and the idea that Earth might not be unique flickered into the realm of possibility. Giordano Bruno, a philosopher ahead of his time, spoke openly of infinite worlds filled with life, an idea so radical it threatened the dogma of his age. He paid with his life, but his vision lingered, a seed waiting for the soil of science to grow. As centuries passed, the search for other worlds moved from philosophy to physics. Isaac Newton revealed the clockwork of the universe, and for the first time, planetary motion could be described not as divine will, but as mathematics. Still, life beyond Earth remained elusive. Telescopes grew sharper, but no alien civilizations waved back. When Percival Lowell peered at Mars in the late 19th century, he thought he saw canals, evidence, he believed, of intelligent beings engineering vast networks to survive a dying world. It was an error, an illusion of optics and imagination, but it ignited the public imagination. For decades, Mars became the stage on which we projected our longing for neighbors in the cosmos. The 20th century brought radio, rockets, and the dawn of modern astronomy. The search for life took on new urgency. In 1961, Frank Drake formulated his famous equation, a framework for estimating the number of civilizations in our galaxy capable of communication. His numbers were guesses, placeholders where knowledge was absent, but the equation itself reframed the problem. Life was not a miracle, it was a probability. Carl Sagan, with his poetic voice, carried this idea to millions, declaring that the cosmos is within us. We are made of star stuff. To Sagan, the search for extraterrestrial life was not just a scientific pursuit, but a profoundly human one, a quest to understand our own place in the universe. Then came Kepler. Launched in 2009, the Kepler Space Telescope was a mechanical prophet, staring unblinkingly into a patch of sky, measuring starlight with inhuman patience. For years, it observed more than 150,000 stars, searching for the telltale dimming that betrayed the presence of planets. The results were staggering. Worlds multiplied before our eyes. Super-Earths, hot Jupiters, mini-Neptunes, rocky planets hugging their stars so closely their surfaces boiled, others drifting in lonely cold orbits at the edges of their systems. The old assumption that Earth-like planets might be rare crumbled. In fact, the galaxy was littered with them. Statistically, there could be billions of rocky, temperate worlds, planets where water could flow and life could, in theory, arise. But statistics alone are not life. For decades, astronomers have struggled with a profound limitation: distance. Light carries information, but only faint whispers of it. To peer into an exoplanet's atmosphere from tens or hundreds of light years away is like trying to read the label on a bottle across a city through heat haze. And yet slowly, methods improved. With transit spectroscopy, astronomers could detect when certain wavelengths of starlight were absorbed as they passed through a planet's atmosphere. Each molecule leaves a unique fingerprint: hydrogen, oxygen, methane, carbon dioxide. They announce themselves in these spectra like colored threads woven into a tapestry. On Earth, these gases are deeply tied to life. A planet with oxygen and methane in balance is not just a planet with chemistry, it is a planet with metabolism, a world breathing. This is the basis of the 98%. Teams of researchers poring over spectroscopic data from observatories like Hubble, ground-based giants such as the Very Large Telescope in Chile, and most recently the James Webb Space Telescope, combined their findings into models. They ruled out natural, abiotic processes that could mimic such signatures. They tested alternative explanations: volcanism, photochemical reactions, exotic chemistry under alien suns. Each possibility chipped away at the probability of life. And yet when all the known alternatives were accounted for, the number that remained, the probability that life is the culprit, rose to heights never before seen: 98%. The figure itself is not magic. It is the product of Bayesian reasoning, a framework that updates probabilities as evidence accumulates. Before these measurements, the prior probability that life existed on this world was vanishingly small, not zero, but unknown. Each new piece of data, each molecule detected, each natural process eliminated, tilted the scales. By the end, the weight of evidence was immense. Of course, astronomers are cautious. Probability is not certainty, and in science, extraordinary claims demand extraordinary proof. Yet even the most skeptical among them could not ignore the numbers. This world is unlike any we have studied before. And it is not only chemistry that excites researchers. The planet itself, as revealed by measurements of its orbit and density, appears strikingly familiar. Roughly the size of Earth, bathed in the light of a star not unlike our own, it sits comfortably in the habitable zone, that delicate band where temperatures could allow liquid water. Its year is not too short, not too long. Its atmosphere is thick enough to shield against radiation, but not so thick as to crush or suffocate. In many respects, it is a mirror, a distant twin to the Earth, a cosmic sibling hidden in the dark. The implications are immense. If life can arise there, then it can arise anywhere. Life would not be a rare miracle bound to the unique history of Earth, but a natural outcome of physics and chemistry repeated across the galaxy. The spark that ignited here may have flickered countless times in countless places. Some of those sparks might have grown into worlds teeming with microbes, some into oceans alive with creatures beyond our imagination, and perhaps somewhere into civilizations capable of building telescopes of their own, wondering, as we do now, if they are alone. Yet this discovery also sharpens the paradox. If life is common, why have we not yet found clear signs of it? Why does the galaxy remain silent? The Fermi paradox looms larger than ever. Perhaps life is abundant, but intelligence rare. Perhaps civilizations bloom and fade quickly, brief lights extinguished before they can cross the gulfs between stars. Or perhaps they are out there now, aware of us, but silent for reasons we cannot yet comprehend. Each possibility carries its own weight of wonder and unease. And so humanity finds itself at a threshold. On one side lies the long history of speculation, myth, and yearning. On the other, the beginnings of knowledge, tentative but powerful. We are not yet at the point of certainty, but the scales have tipped, and for the first time, the balance lies firmly with life. In the quiet darkness of the universe, a new chapter has begun. The question is no longer if life exists elsewhere, but when and how we will confirm it. The planet itself drifts in the silent cradle of its orbit, a world balanced between fire and ice, circling a star that has burned steadily for billions of years. From across the gulfs of space, it is nothing more than a faint shadow against its sun, a whisper in the light curve. Yet through the language of physics, we can reconstruct its portrait. Its host star is a yellow-white beacon, smaller than some, larger than others, not so different from our sun. Its light bathes the planet in a steady glow, neither searing it with lethal radiation nor leaving it in perpetual frost. The orbit lies in that rare and precious zone where temperatures allow the most vital substance of all, liquid water, to endure on the surface. Astronomers call it the habitable zone, but it is more than that. It is the Goldilocks strip of existence, the narrow band where chemistry can breathe. The year of this world is shorter than ours, the orbit tighter, yet not so tight that its skies would be forever locked in tidal embrace. Some exoplanets, trapped close to their stars, always show the same face, one side scorched in eternal day, the other frozen in endless night. This planet, though, spins with freedom. Days and nights alternate, seasons may unfold, weather patterns shift and swirl, It is a world that changes, that breathes in rhythm with its star. The gravity, calculated from its density, is not alien to us. To walk its surface would be to feel a pull only slightly heavier than Earth's, the firm embrace of a planet that could hold oceans, mountains, and an atmosphere thick enough to cradle clouds. Imagine descending through that atmosphere, through layers of vapor tinged with unfamiliar hues. From space, it may appear as a blue-green marble, its oceans glittering beneath veils of clouds. Or perhaps it glows with colors alien to our eyes, turquoise seas of exotic chemistry, coppery continents rich in minerals rare on Earth. The air, we believe, is alive with the chemical signatures of oxygen and methane, not in equilibrium, but in the restless tension that life maintains. On Earth, such a balance is sustained by organisms, plants and microbes exhaling oxygen, animals and bacteria releasing methane. Without life, one gas would smother the other. The numbers suggest that something here is perpetually renewing this imbalance. Something is breathing. We do not yet know if the planet has oceans, though all probability leans that way. Water vapor clings to its spectrum, as if droplets rise and fall in its skies, condensing, raining, evaporating, completing the eternal cycle. If oceans stretch across its surface, they may teem with alien forms, not the towering beasts of imagination, but microbial mats, vast invisible ecologies hidden beneath waves, each organism a thread in the planetary metabolism. Life, after all, does not always roar. It often whispers. It begins at the smallest scale, chemistry wrapped in membranes, replicating, evolving, adapting. If such processes exist here, they may have been unfolding for billions of years, a silent chorus unheard until now. But let us not limit ourselves to the microscopic. Suppose evolution has had the same vast expanse of time here as it has had on Earth. Suppose the wheel of adaptation has turned, generation after generation, in this alien biosphere. What forms might have arisen? The imagination is tempted to populate its forests with strange trees, its skies with winged creatures, its shores with bioluminescent plants. And yet we must be cautious. Life adapts to its environment, and this environment may be vastly different. Its sunlight, though similar to ours, has its own spectral fingerprint. The very color of its sky could alter the course of photosynthesis. Perhaps organisms here are not green, but black, absorbing every photon. Perhaps pigments shimmer in purples and reds, tuned to the star's light. The landscapes could be unlike anything Earth has known, yet bound by the same universal laws of chemistry and evolution. Beyond surface fantasies lies the reality of its climate, a world in balance between heat and cold, where oceans, if present, regulate temperature, where weather cycles may sweep across continents. The greenhouse gases in its atmosphere trap warmth, preventing the world from freezing, but not so much as to push it into runaway heat. Clouds drift in patterns, storms may rage, but the long-term stability of climate is what allows life to persist. On Earth, this stability is guarded by the carbon silicate cycle, the slow breath of rocks and rain, volcanoes and oceans. It is possible that this distant world has its own version of this balance, a geological heartbeat regulating its skies. If so, then it has provided a stable cradle for life across unimaginable spans of time. And what of its star? Stars are the givers and destroyers of worlds. Too large, and they burn their planets with ferocious radiation. Too small, and they flicker unpredictably, bathing planets in flares that strip away atmospheres. This star, however, appears calm, middle-aged, a stable companion. For billions of years it has offered steady warmth, and it will continue to do so for billions more. To orbit such a star is to have time. Time for chemistry to gather into molecules. Time for molecules to dance into life. Time for life to evolve into complexity. The star is not merely a beacon, it is the beating heart of the planetary system, the force that makes habitability possible. If we could stand on the planet's surface, the sky would offer a spectacle both familiar and alien. Its star would hang larger or smaller depending on the orbit's exact distance, a brilliant sun rising and setting over alien seas. At night, constellations entirely unknown would burn overhead, patterns of stars we have never traced. Perhaps its moons, if any, would rise like lanterns, shaping tides, influencing ecosystems. Each detail would shape the world in subtle ways, from the rhythm of its oceans to the behavior of its life. The closer we look, the more uncanny its resemblance to Earth becomes. A rocky planet, liquid water, a breathable balance of gases, a temperate climate, a steady sun. No longer is Earth alone in its role as a cradle of life. For centuries, we believed our planet was unique, a solitary oasis in a desert of rock and gas. Now we see that it may be only one among many. This world, with its 98% chance of life, is not just another data point in astronomy. It is a mirror held across light years, reflecting the possibility that our story is not singular. And yet, we must temper our awe with humility. Our picture of this world is drawn from the faintest of clues, from light so diluted by distance that it arrives at Earth as a trickle, a handful of photons against the noise of the cosmos. We are deciphering its secrets with instruments at the very edge of their power. What we see may shift as new data refines the model. Surprises may await us. For in science, as in life, certainty is an illusion. But even if the details change, the promise remains. This is a world where life is not improbable, but likely. A world that forces us to confront the truth. Earth is not the center of biology. Life belongs to the cosmos. And so we linger on this vision. Alien seas shimmering in starlight, clouds drifting across continents we may never set foot upon, organisms rising and falling in cycles as old as time. A living world, distant yet real. We have not touched it, we may never touch it, and yet it has already touched us. It has changed the way we see the universe and the way we see ourselves. To peer into the secrets of a world light years away is to engage in an act of cosmic detective work, to gather whispers carried across the darkness and weave them into a coherent story. Our only clues are photons, those tireless messengers that depart from a star, travel across space for centuries, and, by chance, strike the mirrors of our telescopes. They arrive faint, scattered, corrupted by the thin veil of Earth's atmosphere. And yet within those delicate patterns of light lies the chemistry of another world, hidden but not silent. The question is how to extract meaning from such fragility, how to transform starlight into knowledge of life. The first great breakthrough came with the transit method, where a planet crossing the face of its star produces a tiny dip in brightness, a subtle flicker that repeats with every orbit. From that flicker, astronomers can measure the planet's size, its orbit, even its density if paired with radial velocity, the wobble of the star caused by the planet's gravitational tug. But the true revolution lies in transit spectroscopy. As the starlight filters through the thin shell of the planet's atmosphere, some wavelengths are absorbed, creating telltale fingerprints. A spectrum, spread out into its rainbow, reveals these absences. Each missing line corresponds to a molecule: hydrogen, oxygen, water vapor, methane. Together, they sketch the invisible outline of an alien sky. On Earth, astronomers built giants to chase these signals. The Keck telescopes in Hawaii, the Very Large Telescope in Chile, instruments that rise like temples beneath the stars. Their mirrors, carved and polished to impossible precision, gather light with the patience of centuries. Even more powerful are the machines humanity has flung beyond Earth's atmosphere, where no air can blur the view. Hubble, once our most trusted eye, captured not only galaxies, but the fragile atmospheres of nearby exoplanets. And then, in the year 2021, came the James Webb Space Telescope, its golden mirrors unfolding in the cold darkness beyond the moon. Webb is no ordinary telescope. It is a time machine and a spectroscope combined, designed to catch the faintest glimmers of infrared light, the very glow of molecules vibrating, the heat of atmospheres circling alien suns. With Webb, the search for life leaped forward. Its instruments can measure the atmospheric composition of planets orbiting stars dozens, even hundreds of light years away. It has already revealed clouds on distant giants, hazes in strange skies, and the chemical fingerprints of water vapor on rocky worlds. When directed at the planet now suspected to host life, it provided the most crucial evidence, a cocktail of gases that defies non-biological explanation. The molecules do not align with equilibrium chemistry. They suggest not stasis, but a system in flux, a system fed by processes that renew and balance, processes that, here on Earth, are driven by biology. But Webb is only the beginning. Humanity's imagination is already reaching further. Engineers and astronomers are designing the next generation of telescopes, instruments so ambitious they verge on science fiction. The Large Ultraviolet Optical Infrared Surveyor, LUVOIR, has been conceived as a space-based leviathan, a mirror many times larger than Webb, capable of directly imaging Earth-like planets. To directly image a planet is to see it not as a shadow, but as a world, to separate its faint glow from the blinding brilliance of its star. To achieve this, astronomers propose a star shade, a colossal, flower-shaped shield flying in formation with a telescope, blocking the star's light so that the planet beside it can be seen. It is a daring idea, requiring spacecraft to dance with precision across millions of kilometers, but if achieved, it would grant us pictures of alien worlds, disks of color, perhaps even glimmers of oceans and continents. On the ground, too, the race continues. The extremely large telescope, under construction in Chile, will boast a mirror 39 meters across, an eye so vast it will drink in starlight with an insatiable hunger. With it, astronomers hope to read atmospheres, track weather patterns, even detect the glow of vegetation like biosignatures. These giants are not just machines, they are extensions of our senses, eyes built to look where human eyes cannot, to stretch our vision across light years. The methods of detection are varied, each a thread in the tapestry of knowledge. Radial velocity, where astronomers measured the star's subtle wobble caused by the tug of a planet's gravity, reveals the planet's mass. Direct imaging, where the light of a planet is separated from its star, offers a glimpse of reflected starlight. Astrometry, the precise mapping of a star's position, can betray the presence of orbiting companions. Each method has its strengths, each a tool to chip away at the mystery. Together, they form a network of confirmation, ensuring that what we see is real, not illusion. Yet even as our instruments sharpen, we remain painfully aware of their limits. The planet that now excites us lies tens of light years away. To send a probe would take tens of thousands of years with current technology. We are bound for now to the tyranny of distance. Our only means of contact is light. And so we become masters of inference, extracting every detail we can from photons. It is a slow, patient science, but it is relentless. With every new telescope, the fog clears a little more. Still, astronomers are cautious. A signal that looks like biology may yet hide an exotic form of chemistry unknown to us. The interplay of geology, atmosphere, and radiation can create surprising imitations. To confirm life beyond doubt will require evidence so strong it silences every alternative. That is why the search is expanding to multiple planets. If we find not one but many worlds with atmospheric imbalances, the statistical case will grow overwhelming. Life, then, would not be an anomaly, but a trend. And there are other strategies. Radio telescopes, like those at the SETI Institute, still scan the skies for artificial signals, for transmissions that could only come from intelligence. So far, the silence persists. But some argue we should broaden our search, not just for radio, but for technosignatures of all kinds. Laser pulses, waste heat from vast machines, even chemical pollutants in exoplanet atmospheres that suggest industry. If biology can leave fingerprints, so can technology. As humanity reaches deeper, the boundary between imagination and engineering narrows. Concepts once relegated to science fiction, vast interferometers spread across space, telescopes built on the moon's far side, fleets of autonomous probes are now entering serious discussion. For the discovery of a 98% chance of life does more than confirm our suspicions. It ignites a hunger. It demands that we look closer, that we invent, that we risk, that we step beyond the limitations of our present. The knowledge that we may not be alone is no longer a philosophical musing, but a scientific imperative. Each new instrument is a bridge, each spectrum a revelation. The cosmos is whispering its secrets, and we, patient and restless, are learning to listen. Somewhere in that faint light lies the answer, waiting for us to gather the courage and ingenuity to claim it. When the announcement first rippled across the world, it was not confined to laboratories, observatories, or the narrow corridors of academia. It leapt into headlines, spilled across living rooms, echoed in classrooms and cathedrals, and lit fires in conversations at kitchen tables. The idea that astronomers had found a planet with a 98% chance of harboring life did not simply enlarge our scientific horizons. It struck at the very foundations of what it means to be human. For centuries, the question of our aloneness had hovered at the edges of thought. Philosophers speculated, religions interpreted, poets dreamed, but there was always the shield of uncertainty. Suddenly, that shield was gone. Suddenly, the cosmos was no longer silent. Suddenly, we were part of a larger story. Reaction spanned the spectrum of human emotion. For some, it was elation, an expansion of the imagination so profound that tears came easily. To know that life thrives beyond Earth is to feel less isolated, less fragile, less of a miracle in a void. It reframes Earth not as a singular oasis, but as one flower in a galactic meadow. For others, the revelation was unsettling, even frightening. The thought that biology, perhaps even intelligence, might exist just across the cosmic sea raised ancient fears. What if they are hostile? What if they are greater? What if humanity's fragile dominion on Earth is only a fragile spark against the immensity of life elsewhere? Awe and anxiety, wonder and dread, they mingled together, just as they did when Copernicus displaced the Earth from the center of the cosmos, or when Darwin revealed our kinship with every creature. Religion, too, felt the tremors. In churches, temples, and mosques, leaders grappled with the implications. Some embraced the discovery as a testament to the boundless creativity of the divine, a cosmos so vast and fertile it could not help but bring forth life in myriad forms. Others struggled, for doctrines built on human uniqueness suddenly had to accommodate alien kin. And in quiet corners, individuals felt their faith tested, stretched, or renewed. The discovery did not resolve the ancient tension between science and spirituality, but it forced both to expand their horizons. To imagine life on another planet is to confront the question of universality. If we are made in the image of something greater, then so too might they be. If redemption, morality, or purpose exists, does it stretch across stars? Philosophers, meanwhile, dusted off old arguments with new urgency. The anthropic principle, the idea that the universe must allow observers because we exist to observe it, now faced a revision. If life is common, perhaps intelligence is inevitable. Perhaps consciousness is not a singular accident, but a pattern the cosmos repeats. Or perhaps intelligence blooms often, but burns quickly, civilizations rising like sparks and vanishing before they can bridge the void. The Fermi paradox sharpened. If life is so probable, why the silence? Are we listening incorrectly? Or are there reasons for the quiet? Each possibility, that civilizations hide, or perish, or communicate in ways we cannot yet perceive, reframed humanity's place. We were no longer asking, are we alone, but where is everyone? In the arts, the discovery ignited a renaissance. Musicians composed symphonies inspired by the thought of alien skies, painters imagined forests of crystal trees or oceans alive with luminescent creatures. Writers, long accustomed to weaving fiction from speculation, suddenly found themselves humbled by the knowledge that their imaginings were no longer merely fanciful, but perhaps, somewhere, real. Cinema, literature, visual art, all absorbed the revelation, and in doing so, reshaped culture. For once, humanity's myths could be enriched not by fantasy alone, but by the faint glow of scientific truth. Children, too, felt the change. In schools, where once the question of alien life was a speculative exercise, now it became a practical topic of study. Teachers described not just the possibility of life, but the likelihood. Students sketched aliens not as distant impossibilities, but as inevitable participants in the grand narrative of the cosmos. For a new generation raised with the near certainty of life beyond Earth, the universe would never again feel empty. Dreams of exploration, of contact, of travel between stars became less like fiction and more like destiny. Yet the cultural impact went deeper still. Nations pondered what it meant for humanity's identity. For centuries, divisions of race, religion, and nationality have fractured our species, setting us against each other. But with life beyond Earth looming as near certainty, a subtle shift occurred. The boundaries between nations seemed smaller, the shared identity as Earthlings more pronounced. For the first time in history, humanity's us stretched beyond the planet itself. If we are not alone, then Earth is no longer just a collection of countries, but a single community among the stars. This realization did not erase conflict, but it whispered of unity, of a broader perspective where our differences shrank before the immensity of the cosmos. In politics, the implications were profound and practical. Governments asked how such knowledge should shape priorities. Should exploration be accelerated, funds redirected to space programs, international cooperation enhanced? Should we attempt to send signals, to declare our presence? Or should we remain silent, cautious of who or what might listen? These debates were not new. SETI had pondered them for decades, but never before had they carried such urgency. The abstract had become concrete. The stakes were no longer hypothetical. For the individual, the emotional resonance was intimate. To walk outside and look up at the stars, knowing that one of them hosts a world alive, transformed the night sky. Each point of light became a question mark. each constellation a possibility. Some felt smaller, dwarfed by the immensity of life's spread. Others felt larger, as if life's presence elsewhere validated our own, weaving us into a cosmic fabric. The discovery did not simply expand space, it expanded meaning. And yet, alongside wonder, there was caution. If life exists there, then we must reckon with its forms. Perhaps it is microbial, unseen but thriving, reminding us that life's essence is persistence, not grandeur. But perhaps it is complex. If evolution has played out across eons, then forests may sway under alien suns. Oceans may roar with creatures unlike any Earth has known. The possibility of intelligence cannot be ignored. And with it comes the greatest question of all. If we are not alone, then what responsibilities do we bear? How should we approach? What should we say? What silence should we keep? In this way, the discovery did more than alter science. It altered selfhood. Humanity for the first time was forced to see itself not as a solitary species on a solitary rock, but as part of a larger cosmic ecology. The perspective was humbling, exhilarating, destabilizing. Our myths, our sciences, our arts, our politics, our philosophies all found themselves pulled into orbit around a single revelation, that somewhere, on a world that circles a distant sun, life breathes, and with that breath, the universe itself seems more alive. Skepticism has always been the guardian of science, the voice that tempers awe with caution, that insists on rigor when enthusiasm threatens to outpace evidence. And so, when astronomers announced that a distant planet showed a 98% likelihood of harboring life, not everyone embraced the finding as a revelation. In observatories and universities, in journals and conferences, a chorus of doubts rose. Could the signal be an illusion? Could the atmosphere we think we see be an artifact of instruments or the product of unfamiliar, lifeless chemistry? The numbers were thrilling, yes, but numbers can deceive, and history has warned us against premature certainty. The first and most immediate counter-argument was methodological. Spectroscopy, though powerful, is exquisitely sensitive to noise. The starlight we study arrives faint, filtered through interstellar dust and then through our own atmosphere when captured by ground-based telescopes. Even space telescopes, pristine in orbit, must grapple with instrument imperfections, detector noise, calibration errors. Could the signatures of methane, oxygen, and water vapor be misinterpretations of subtle distortions? Could tiny misalignments mimic a biological fingerprint? Some scientists argued for caution until the data could be confirmed by multiple independent instruments, ideally with different methods. In science, replication is the final arbiter. Others raised geological counter-arguments. On Earth, methane paired with oxygen suggests biology because life maintains the imbalance. But what of alien geology? Could there be processes unknown to us, mechanisms that generate methane abiotically while preserving oxygen? For instance, intense volcanism, interacting with water and exotic minerals, might sustain unusual chemical balances. Or ultraviolet radiation from the star might drive photochemistry we do not yet fully understand. Life is not the only source of disequilibrium. Geology, chemistry, and radiation can conspire in ways unfamiliar to terrestrial experience. Skeptics reminded us that the cosmos is stranger than we assume, and that Earth's patterns cannot always be the universe's rule. Some critics focused on the probability itself. 98% is a seductive number, but what does it mean? Probabilities in science are not certainties, they are models dependent on assumptions. If the assumptions are flawed, the numbers are illusions. The Bayesian frameworks used to calculate the likelihood of life depend on priors, starting beliefs about how common life is, how atmospheres evolve, how gases interact. Change the priors, and the probability can shift dramatically. What looks like 98% under one model might collapse to 50% or less under another. Numbers feel precise, but behind them lie judgments, choices, interpretations. Then there is the shadow of history. Astronomy has known false dawns before. Lowell's canals on Mars were illusions, born from the eye's longing to impose order on blur. The discovery of pulsars in 1967, rapidly blinking radio signals, at first seemed so artificial they were jokingly labeled LGM, for little green men. They turned out to be neutron stars, natural and extraordinary, but not alive. More recently, the case of phosphine on Venus reminded us of science's pitfalls. In 2020, researchers announced detection of methane gas in the Venus atmosphere, a molecule difficult to explain without biology. It was heralded as a potential sign of life in the clouds of our sister planet. But soon other scientists challenged the data, reanalyzed the spectra, and argued that the signal might have been noise or misinterpreted sulfur dioxide. What began as a possible breakthrough devolved into controversy. Skeptics now point to Venus as a warning: extraordinary claims require extraordinary patience. Even if the signatures are real, even if the chemistry is correctly interpreted, life itself is slippery to define. On Earth, life is a cycle of replication, metabolism, and evolution built upon DNA and proteins. But elsewhere, the architecture could be different. Could there be forms of chemistry that mimic biological imbalances without true biology? Could self-sustaining but non-living processes trick our instruments? Some biochemists caution that we must be wary of false positives, phenomena that resemble life without being alive. Our definition of life may be too narrow or too Earth-centric to capture what truly exists on alien worlds. There is also the question of bias. Humanity desperately wants to find life elsewhere. It is one of the deepest longings of our species. Such longings can subtly influence interpretation, pushing scientists to favor life-based explanations over lifeless ones. Even with the strictest controls, enthusiasm can color judgment. Skeptics warn of confirmation bias, the risk that we see what we want to see. To guard against this, they argue that the community must demand higher standards of proof, resisting the temptation of headline-driven certainty. Yet even among skeptics, there is acknowledgement of progress. Whether or not the 98% holds, whether or not this particular planet proves to be alive, the methods that produce the claim are real and powerful. They mark a new era where life signatures can be sought systematically, where atmospheric chemistry can be dissected across the galaxy. Skeptics may doubt this case, but they rarely doubt the trajectory. The tools will improve, the data will accumulate, and sooner or later, one signal will withstand every criticism. Skepticism is not the denial of possibility, but the demand for truth. This tension between believers and skeptics is the lifeblood of science. Enthusiasm propels us forward, but skepticism keeps us grounded. Together, they form the balance that prevents science from drifting into fantasy while ensuring it does not calcify into cynicism. In the debate over this planet, the dynamic is vivid. Optimists argue that we have glimpsed life's first true signal beyond Earth. Skeptics counter that extraordinary claims remain unproven. Between them lies the exhilarating tension of discovery, the sense that we are poised on the edge of revelation. And there is another possibility, more subtle but perhaps more profound, that both sides are right. Perhaps the signals are real, the gases genuine, the chemistry unusual, but our interpretation of life is too narrow. Perhaps what we are detecting is not life as we know it, but something adjacent, something stranger, something that forces us to redefine the very concept. Life might not be binary, but a spectrum, a gradation from chemistry to biology, from reaction to evolution. In glimpsing this world, we may be seeing not a mirror of Earth, but a new category altogether. A reminder that the cosmos is not obliged to conform to our definitions. Thus the debate rages on, not as a hindrance, but as a sign of vitality. Science advances not by consensus alone, but by argument, challenge, refinement. The 98% figure may endure, or it may erode under scrutiny. The planet may one day be confirmed alive or revealed as a false signal, but either way, the process itself is progress. The skepticism, the caution, the relentless questioning, these are not obstacles to discovery. They are the very tools that ensure when discovery comes, it will be real, unshakable, and transformative. The discovery of a world that may be alive has not only transformed our understanding of the cosmos, it has begun to reshape our ambitions. In laboratories, space agencies, and think tanks across the globe, the announcement has electrified a new generation of explorers. For decades, space missions were driven by curiosity, by the urge to map planets, measure atmospheres, and test theories. Now, for the first time, they are driven by something more urgent: confirmation. The existence of a planet with a 98% chance of harboring life is not simply a tantalizing hint, it is a summons, a call to build the machines that can carry us from probability to proof. The first wave of this response is already visible. Proposals that once lingered as distant dreams on the desks of engineers have surged to the forefront of funding debates. The James Webb Space Telescope, for all its brilliance, was never designed to be the final word on exoplanet life detection. Its successors are waiting in blueprints. The LUR mission, conceived as a behemoth telescope with a mirror up to 15 meters across, could capture spectra of dozens of Earth-like planets, dissecting their atmospheres with exquisite precision. HABEX, the Habitable Exoplanet Observatory, would be smaller but focused entirely on one purpose: to find and study worlds like our own. Both concepts rely on technologies such as star shades or coronagraphs, devices that can blot out a star's blinding glare to reveal the faint glow of its planets. With them, astronomers would not merely infer life from chemistry, they might glimpse weather systems, seasonal changes, perhaps even the subtle colors of alien vegetation. On the ground, the drive is equally fervent. The extremely large telescope in Chile, its vast 39-meter mirror nearing completion, promises to be the most powerful eye ever turned to the skies from Earth's surface. Alongside it, the giant Magellan telescope and the 30-meter telescope will open new windows, their adaptive optics canceling the blurring of the atmosphere to deliver clarity once thought impossible. Together, these terrestrial giants will form a network of confirmation, cross-checking the signals from space telescopes, probing the atmospheres of nearby Earth-sized worlds, and perhaps even detecting the glimmer of oceans reflecting starlight. Each is a cathedral to curiosity, but also a workshop of truth, designed to test the extraordinary claim of life. Yet even these are stepping stones. The challenge of interstellar distance looms immense. The planet in question lies dozens of light-years away. At the speeds of current spacecraft, a probe would take tens of thousands of years to arrive. And so visionaries turn to bolder concepts. Breakthrough Starshot, a project born from the imagination of physicists and backed by private investment, envisions sending fleets of tiny probes propelled by immense ground-based lasers. Each probe, no larger than a postage stamp, could be accelerated to 20% of the speed of light. At such speeds, the journey to the nearest stars would shrink from millennia to mere decades. The idea is audacious, fraught with engineering challenges, but it represents the first serious attempt to contemplate reaching other stars within human timescales. With a world that may harbor life within reach, the incentive to refine such concepts grows urgent. Others imagine slower, grander journeys. Fusion-powered starships, solar sails spanning kilometers, or generational vessels where entire societies might live and die en route to another sun. These ideas remain speculative, sketches in the margin of possibility. But what was once mere science fiction now gains a new gravity. For if life exists within our neighborhood, if biology thrives on planets not so different from our own, then the question is no longer whether to go, but how and when. The discovery has transformed interstellar travel from fantasy into necessity. Even if it takes centuries, even if it requires leaps of technology as radical as fire or flight, the lure of confirmation, of standing on alien soil and hearing life breathe, is irresistible. Closer to home, missions are reimagined with this new perspective. The study of exoplanets has largely been indirect, focused on light curves and spectra. But astronomers now propose missions that could map exoplanets the way Galileo mapped Jupiter's moons or Cassini mapped Saturn's moons. Interferometers spread across space, combining light from multiple satellites to create images of alien worlds with unprecedented sharpness. Telescopes stationed on the far side of the moon, shielded from Earth's radio noise, to scan the skies for techno-signatures, artificial signals, industrial gases, even the thermal glow of vast machines. Each concept, once shelved for lack of urgency, now surges with momentum. The planet with its 98% chance of harboring life has provided the spark. Beyond science and engineering, there is strategy. Nations are aware that the first to confirm extraterrestrial life will secure not only prestige, but a legacy written in history. Space exploration, once a Cold War competition, is now a stage for global cooperation and rivalry. The United States, Europe, China, India, and private companies all see in this discovery an opportunity, a new space race, not for territory, but for truth. Some argue for collaboration, for pooling resources into international missions that no single nation could achieve alone. Others whisper of competition, of secret projects, of the immense cultural and political power that would come with unveiling the first undeniable proof of life. The future of exploration may be shaped as much by politics as by technology. Meanwhile, the debate over messaging grows louder. If the planet is alive, should we try to reach out? Should we send signals, beams of radio or laser light carrying greetings across the void? Or should we remain silent, cautious of what ears might listen? Advocates of messaging extraterrestrials argue that silence is arrogance, that if life is out there, it deserves to know it is not alone. Critics counter that to announce our presence is to court danger, to invite the unknown. The planet's discovery has breathed new urgency into these arguments. We are no longer asking whether others exist, but how we should behave when they do. Even as we dream of journeys and debates over signals, a quieter revolution is unfolding. The knowledge that life almost certainly exists elsewhere changes how we approach our own planet. Earth, once unique, is now one among many. Its fragility becomes clearer, its value sharper. To explore other worlds is to reflect on our own. To search for life is to realize that we are stewards of life already. The pursuit of the distant sharpens our awareness of the near. Perhaps in preparing to reach out across the stars, we will finally learn to care for the oasis beneath our feet. Thus, the discovery is not a conclusion, but a catalyst. It propels us to build telescopes beyond imagination, to craft starships out of dreams, to argue over risks and hopes, to reconsider our unity and our responsibilities. It is shifted exploration from curiosity to destiny, Somewhere out there, on a planet that circles a star like ours, life may already be looking up at its own sky. Perhaps it too wonders the same questions. Perhaps it too has built instruments to measure light, to search for neighbors. And perhaps one day our questions will meet in the middle, across the vast sea of stars. When we speak of life on a distant planet, it is tempting to imagine familiar shapes. Forests of green, seas teeming with creatures not unlike fish, skies alive with bird-like wings. But such imaginings are earthbound, sculpted by the specific accidents of our evolution. Chlorophyll tuned to our sun's spectrum, skeletons built from calcium, bodies shaped by gravity and air density. To contemplate life on another world is to step into a realm where nature's creativity may be bound only by physics and chemistry, not by terrestrial precedent. And so we must begin with humility, acknowledging that our imaginations may falter before the true diversity of life in the cosmos. Yet, guided by science, we can at least sketch plausible outlines of what might breathe beneath that alien sky. At the most basic level, life requires energy, a solvent to enable chemistry, and a stable environment in which molecules can interact. On Earth, water plays the role of the universal solvent, carrying nutrients, dissolving gases, enabling the dance of molecules that gave rise to life. If, as the data suggest, this planet harbors oceans and an atmosphere rich in water vapor, then water-based life is the most straightforward possibility. Microbes, invisible to the naked eye, could be thriving in vast numbers, forming mats on rocks, drifting in plankton-like blooms across alien seas, or clustering around nutrient sources in soils. Such organisms would be the pioneers, the first engines of planetary metabolism. Like Earth's cyanobacteria billions of years ago, they could exhale gases, altering the atmosphere in ways detectable across light years. From microbes, complexity may follow. Evolution is an opportunist, taking whatever structures exist and reshaping them into new forms. If photosynthesis or its alien equivalent has arisen, then the planet may be covered in organisms that capture starlight. But here the details diverge from Earth. The spectrum of the host star is slightly different from our sun's, its light skewed toward certain wavelengths. On Earth, chlorophyll absorbs red and blue light, reflecting green, giving plants their color. On this planet, photosynthetic pigments may adapt differently. Perhaps foliage here is purple, absorbing the star's peak output. Perhaps it is black, a perfect absorber, drawing in every photon. Imagine walking across an alien plain, where fields of obsidian-colored vegetation shimmer under the sun, or forests glowing faintly with bioluminescence as night falls, each leaf a lantern. In the oceans, if oceans there are, life may take forms that defy our assumptions. On Earth, buoyancy allows creatures to grow vast without the constraints of gravity. Whales, giant squid, schools of fish moving as one. On this planet, with slightly stronger gravity, the oceans may be denser, currents stronger, shaping life into forms built for resilience and endurance. Creatures might grow with wide, flat bodies to resist pressure, or evolve buoyant sacs filled with gases rare in the water. If the chemistry differs, entire ecosystems might operate on cycles of sulfur or ammonia rather than carbon dioxide. The alien seas could glow at night with the sparks of bioluminescent organisms, waves shimmering as if lit by stars beneath the surface. On land, gravity again plays its role. Slightly stronger than Earth's, it would press creatures lower to the ground, encouraging sturdy builds. Towering trees might be rare. Instead, broad, squat vegetation could dominate, leaves sprawling like shields to capture light. Animals, if they exist, might move closer to the Earth, with strong limbs built to resist the pull of gravity. Wings might be rarer, flight more difficult in heavier air, unless the atmosphere is denser than Earth's, in which case flight could be easier. Creatures soaring on broad membranes, gliding between cliffs and valleys. Imagine landscapes where forests are carpets of purple moss stretching to the horizon and dotted with luminous fungi-like pillars, and across them glide leathery winged creatures, silent shadows drifting under a star unlike our own. But we must not assume that life elsewhere would necessarily mirror our familiar categories of plants and animals. It may be stranger. On Titan, Saturn's moon, lakes of methane lap against icy shores. Scientists speculate about the possibility of methane-based life, using hydrocarbons as a solvent instead of water. If such life can exist there, then perhaps on this distant exoplanet, alternative chemistries may flourish. Silicon, though less versatile than carbon, might support polymer-like structures. Ammonia, though less efficient than water, might enable metabolic cycles. Life may not be composed of cells at all, but of networks, filaments, colonies that spread across rocks like living webs. On Earth, even here, slime molds remind us that intelligence can emerge from collective behavior, that life does not need nervous systems to coordinate and adapt. The most provocative question, of course, is whether life evolution has had the time and opportunity to give rise to intelligence. On Earth, for 4 billion years, life remained microbial. Complex multicellular organisms only appeared in the last 500 million years, and intelligence capable of technology in the last few million. It may be that intelligence is a rare accident, requiring chains of chance events, mass extinctions, evolutionary bottlenecks. Or it may be that intelligence is a natural outcome of complexity, that once ecosystems become rich enough, minds emerge to navigate them. If the latter, then somewhere on that world, beings may exist who look up at their sky, wonder at the stars, and ask the same questions we do. They might build their own telescopes, peer into their heavens, and perhaps at this very moment be calculating the probability that life exists around a star they see shining faintly in their night sky, our sun. Yet, we must also reckon with the possibility that life there is not like life here at all, that our categories of microbial and complex are insufficient. Life might be symbiotic at its core, organisms blending into ecosystems so thoroughly that the distinction between individual and environment blurs. Imagine plains where the soil itself is alive, networks of organisms exchanging signals and nutrients, landscapes that pulse and shift like the surface of a brain, or seas where creatures are not discrete but part of a vast, living web, their bodies connected by filaments spanning kilometers. Intelligence, if it arises in such systems, might not be concentrated in individuals, but distributed, a planetary mind whispering through networks of biology. The challenge is that we cannot yet know. Our instruments show only chemical imbalances, suggestive but silent about form. They whisper that life breathes, but not what shape that life takes. Our imaginations fill the void, sketching forests of black plants, oceans of glowing organisms, landscapes alive with alien beauty. But imagination must be tethered by science, by the constraints of physics, chemistry, and evolution. Whatever thrives there must obey those laws, and in obeying them, it may resemble us in surprising ways, or diverge into forms so strange that when we first see them, we will struggle to call them life at all. Still, one truth emerges. If life exists there, it has endured. To alter a planet's atmosphere, to leave signatures detectable across light years, requires scale, persistence, stability. It means ecosystems vast enough to reshape skies, cycles strong enough to endure for millennia. Life there is not fragile. It is planetary. And in that endurance lies a message that the universe is fertile, that biology is not confined to one world. Somewhere across the abyss, another planet breathes. And whatever its life looks like, it proves that we are not the sole expression of nature's creativity. For centuries, humanity's gaze turned outward to the stars, but our first and most immediate frontiers of exploration lie close to home. The solar system itself is a gallery of worlds, each with its own story, its own potential for life. Long before astronomers glimpsed the chemical whispers of life on a planet dozens of light years away, we dreamed of neighbors much closer, on Mars, beneath the ice of Europa, in the geysers of Enceladus, in the alien lakes of Titan. The revelation that life may thrive beyond our sun does not diminish these quests. On the contrary, it sharpens them, reframing our local searches as part of a grander narrative. If life is probable out there, then surely it must be possible here, in the shadows of our own celestial backyard. Mars has always been the first suspect. For generations, it was the archetype of the other world, dry, red, and mysterious. The canals imagined by Lowell turned out to be illusions, but the allure persisted. Today, rovers crawl across its plains, drilling into rocks, sifting soil, analyzing with instruments that once would have filled entire laboratories. They search not for civilizations, but for biosignatures, fossilized microbes, chemical traces of metabolism, whispers of organic molecules locked in ancient sediments. Mars, we now know, once had rivers, lakes, and perhaps even oceans. Its valleys were carved by flowing water, its rocks weathered in currents that no longer run. If ever there was a time when Mars could host life, it was billions of years ago. The question is whether any trace of that life remains, dormant beneath the surface, waiting in icy aquifers, or written in microscopic fossils. Each discovery of organic molecules, each measurement of methane plumes in the atmosphere keeps the question alive. If we confirm life on Mars, even microbial, long dead, it would prove that biology is not unique even within one solar system. Yet Mars is not alone in its promise. Farther out, in the cold realm of the gas giants, lie icy moons that defy expectation. Europa, moon of Jupiter, is a frozen world, its surface a cracked shell of ice. Yet beneath that crust, scientists are convinced lies a global ocean, kept liquid by tidal forces that flex and warm the moon's interior. In that ocean, more water exists than in all of Earth's seas combined. Hydrothermal vents may line its sea floor, spewing minerals and energy into the darkness, just as they do on Earth's ocean floors, vents where life here thrives without sunlight, nourished by chemistry alone. If life can arise independently in Europa's ocean, then it would be a profound revelation. Two origins of life in one planetary system. Probes are already planned. NASA's Europa Clipper, launching in the coming years, will skim close to the moon, its instruments searching for plumes of water erupting through cracks in the ice, analyzing them for organic chemistry, perhaps even biosignatures. Nearby, Saturn's moon Enceladus offers an even more dramatic invitation. Its icy surface hides a subsurface ocean too, but unlike Europa, it vents its secrets openly. Great geysers erupt from fissures near its south pole, spraying water vapor, salts, and complex organic molecules into space. Cassini, before plunging into Saturn's atmosphere in a final blaze, flew through these plumes, tasting their chemistry. What it found astonished scientists, not only water and organics, but signs of hydrothermal activity, the very conditions on Earth's ocean floors where life began. Here in Enceladus' hidden seas, the ingredients for life seem complete: liquid water, energy, organics. To capture and analyze those plumes with more advanced instruments is a tantalizing prospect. A single mission, a fly-through, could one day answer one of humanity's oldest questions. And then there is Titan, Saturn's largest moon, a world stranger than any earthly dream. Beneath its orange haze lies a landscape of methane rivers, lakes, and seas, carved into icy plains. It is the only other body in the solar system with stable liquid on its surface. But its chemistry is exotic. Liquid methane and ethane flow where water would flow on Earth, sculpting shorelines and deltas. Titan is a laboratory of prebiotic chemistry, where organic molecules rain from the sky, settle into lakes, and perhaps assemble into structures unlike anything we know. Life here, if it exists, might be utterly alien, built not on water but on hydrocarbons. The Dragonfly mission, a nuclear-powered drone, is set to explore Titan's skies and surface in the 2030s, sampling, analyzing, and flying from dune to delta. Its discoveries may show us how life might look when freed from the template of Earth. Each of these worlds carries within it a fragment of the great puzzle. If life is found on Mars, Europa, Enceladus, or Titan, it would mean that biology is not rare, not a fluke, but a natural outcome of chemistry wherever conditions allow. And that knowledge would intertwine with the distant discovery of life on an exoplanet. Together, they would paint a picture of a living cosmos, where life arises independently in multiple places. Earth would no longer be the miracle, but part of a pattern. The message would be unmistakable. Given time and the right ingredients, life is inevitable. And yet the searches within our solar system differ in one crucial respect from those across the galaxy: proximity. Mars is a few months away by rocket. Europa, Enceladus, Titan, a few years. We can send machines to them, not just photons. We can drill, fly, taste, analyze. Here, probability becomes proof. To find life within our solar system would be to touch it, to examine it under microscopes, to sequence its chemistry, to ask the most profound question: is it like us, built on DNA, or is it utterly different? If life here shares our biochemistry, it might suggest a common origin, perhaps through meteorites carrying seeds between planets. But if it is different, if Mars life or Europa life uses alien molecules, alien genetic codes, then we will know beyond doubt that the universe births life not once, but many times. The consequences would reverberate across every discipline, every philosophy, every heart. The pursuit of life in our solar system and beyond are no longer separate quests, but complementary. Each discovery feeds the other. If a distant exoplanet shows hints of life, it sharpens our drive to confirm biology nearby. If we find microbes beneath Mars's soil, it lends weight to the signals we detect across light years. The cosmos is no longer a set of disconnected mysteries. It is a continuum, from the deserts of Mars to the oceans of Europa to the faraway planet circling its star in silence. Each is a clue, each a piece of the tapestry, each a step toward the realization that life is woven into the very fabric of the universe. Thus, the search for life has become a symphony, with instruments spread across worlds near and far. Rovers, orbiters, telescopes, future starships, all part of the same song, each verse echoing the same refrain. Life is possible, perhaps inevitable, wherever conditions allow. And with every mission, every photon, every grain of dust analyzed, we move closer to the moment when possibility becomes proof. When humanity at last can say with certainty, we are not alone. From the moment we first tuned our radios to the sky, humanity has wondered if another intelligence might be listening too. In 1960, in a small radio telescope in West Virginia, an astronomer named Frank Drake pointed an antenna at two nearby sun-like stars and listened. His experiment, called Project Ozma, was simple in conception but revolutionary in spirit. If intelligent beings exist beyond Earth, perhaps they too use radio waves, and perhaps we might overhear them. For weeks, Drake's telescope swept the heavens, ears pressed against the cosmic static. He heard nothing, but he had opened a door. That door became SETI, the search for extraterrestrial intelligence, and it would grow into one of humanity's most ambitious scientific endeavors. For decades, SETI has listened. Giant dishes like the late Arecibo Observatory in Puerto Rico scanned the skies for narrow-band signals, the kind unlikely to arise from nature. The Allen Telescope Array in California, funded by both public and private sources, still listens, searching thousands of stars. Other efforts piggyback on astronomical observations, analyzing the flood of data collected for other purposes. The silence has been profound. No clear, deliberate message has ever arrived. And yet scientists persist because the possibility is so profound that even silence teaches us something. The absence of signals constrains theories, forcing us to wonder, are civilizations rare, or are they shy, or do they speak in ways we cannot yet comprehend? The discovery of a planet with a 98% chance of life has breathed a new urgency into this search. For decades, SETI faced skepticism, even ridicule. Critics called it a lottery with impossible odds, chasing ghosts across the cosmos. But now, the numbers tell a different story. If life is almost certain on a nearby world, then intelligence too cannot be ruled out. The planet becomes not just an object of atmospheric study, but a target for SETI's ears. Radio telescopes turn their dishes toward its star, straining to catch any whisper, any irregularity in the static. Optical SETI experiments, which search for laser pulses, focus there as well. The idea is simple. If another civilization exists, perhaps it too has wondered. Perhaps it too has built telescopes and transmitters, and perhaps, just as we listen, they transmit. The notion of technosignatures has expanded far beyond radio. Scientists now consider all the ways technology might reveal itself across interstellar distances. Artificial lights on a planet's dark side could betray cities. Pollutants in an atmosphere, chlorofluorocarbons, nitrogen oxides, could signal industry. Vast megastructures orbiting stars, so-called Dyson spheres, might dim or alter a star's light in ways detectable from Earth. Waste heat emitted by large-scale technology could appear as infrared excess around a planet. Even gravitational anomalies might betray engineering on cosmic scales. Each of these possibilities, once fanciful, is now a line of research fueled by the realization that we are no longer chasing fantasies, but exploring probabilities. The most dramatic episode in SETI's history remains the WOW signal of 1977. For 72 seconds, a radio telescope at Ohio State University detected a powerful, narrow-band signal from the direction of the constellation Sagittarius. It was so striking that the astronomer on duty, Jerry Amon, circled it on the printout and scribbled "WOW" in the margin. Yet it was never heard again, despite countless attempts. To this day, the WOW signal remains unexplained, an enigma perched between noise and message. For some, it was a tantalizing brush with another mind. For others, it was a reminder of how easily coincidence can seduce us. The discovery of the 98% planet has rekindled interest in such mysteries, urging scientists to revisit old data, to refine searches, to cast wider nets. SETI today is no longer a marginal science. It is increasingly integrated with mainstream astronomy, bolstered by computing power that can sift petabytes of data for anomalies. Machine learning algorithms scour the skies, hunting for patterns no human could detect. Citizen science projects invite the public to participate, training eyes and ears across the globe. The discovery of a near-certain life-bearing planet has given SETI not just legitimacy, but momentum. What once seemed speculative now feels inevitable. If life is common, then intelligence may be as well. And if intelligence is common, then communication, deliberate or accidental, may already be in the air, waiting to be found. Yet the silence persists, and with it, the paradox. If life is so likely, why has no one spoken? The Fermi paradox looms larger than ever. Perhaps civilizations are rare or fragile, their lifespans too short to overlap. Perhaps they choose silence, wary of predators in the dark. Or perhaps we are listening in the wrong way, at the wrong times, with the wrong assumptions. The discovery of this planet has not solved the paradox, it has sharpened it. It forces us to reconcile two truths. Life appears probable, yet intelligence remains unseen. Somewhere between these truths lies an answer that may redefine our place in the cosmos. And there is a deeper question. Should we speak? The debate over messaging extraterrestrial intelligence, or METI, has grown more urgent. Advocates argue that silence is arrogance, that if civilizations are listening, they deserve to know they are not alone. Sending messages, they say, is a gesture of cosmic kinship. Critics counter that to announce ourselves is to invite risk. We do not know who might be listening or what their intentions might be. The planet, with its 98% chance, forces this debate from philosophy into policy. If there is life, even intelligent life within reach, should we introduce ourselves? Should we beam greetings across the void or remain hidden, listening quietly from the shadows? The discussion is not merely academic. Some have proposed targeted transmissions to this very planet, coded messages sent by radio or laser, carrying mathematics, art, and language. Others urge restraint, arguing that even if intelligence exists there, it may be at a stage far behind us or far ahead. To reveal ourselves without understanding could be to alter their destiny or ours. The stakes are immense. Contact, if it comes, would not be an experiment, but a transformation, changing both species forever. Meanwhile, SETI's scope is expanding beyond individual stars to galactic scales. Surveys of entire regions, searches for patterns in stellar light curves, analyses of unexplained phenomena, all fall under the banner of techno-signature research. The discovery of a planet likely alive has galvanized these efforts, uniting them with astrobiology, planetary science, and exoplanet astronomy. No longer is SETI a fringe pursuit. It is the natural extension of the same impulse that drives us to probe atmospheres and measure spectra. Life and intelligence are no longer separate quests, but two facets of the same search. And so, as radio dishes sweep the skies and telescopes dissect starlight, humanity waits. We wait not in silence, but in expectation, our machines straining for whispers, our imaginations reaching across the gulf. The discovery of life-bearing worlds has shifted the odds. The silence may break tomorrow, or in a century, or never. But the search continues, fueled by the possibility that one day, through the static, through the hiss of the cosmos, another voice will rise, and for the first time in history, we will know we are not the only minds that dream beneath the stars.
To understand why astronomers dare to place such a bold probability on life elsewhere, we must turn inward, back to the story of life on Earth, to the moment when chemistry first crossed the threshold into biology. For if we can trace the path that led from inert molecules to living cells here, then perhaps we can glimpse the paths it might take on other worlds. The origin of life is one of science's most tantalizing mysteries, not yet solved, but illuminated by fragments of evidence, by experiments that recreate ancient conditions, by whispers preserved in rocks billions of years old. The Earth formed 4.5 billion years ago, a young world of molten rock bombarded by asteroids, wrapped in a toxic atmosphere of carbon dioxide, nitrogen, and water vapor. There were no continents as we know them, only volcanic islands, restless oceans, and skies streaked with lightning. In such a world, life seems improbable. And yet, within a few 100 million years, evidence of microbial activity appears in the geologic record. Stromatolites, layered structures built by microbial mats, still stand as silent monuments to Earth's earliest inhabitants. Life began not in a paradise, but in chaos, in a world hostile and violent. This fact alone reshapes our perspective. If life could take root there, under such conditions, then perhaps it can emerge under far more varied circumstances than we imagine. The question, of course, is how? How did lifeless matter organize itself into the first cells? One hypothesis is the primordial soup envisioned by Alexander Oparin and J.B.S. Haldane in the early 20th century. They proposed that Earth's early oceans, rich in simple molecules, became a chemical cauldron energized by sunlight and lightning. In 1953, the famous Miller-Urey experiment tested this idea. By circulating methane, ammonia, water, and hydrogen through sparks of electricity, Stanley Miller produced amino acids, the building blocks of proteins. It was a revelation. Life's ingredients could form spontaneously from chemistry. Since then, experiments have produced nucleotides, lipids, sugars, all the molecular alphabet of biology, under conditions thought to mirror early Earth. But ingredients alone do not make life. They must assemble into systems that store information, replicate, and evolve. Many scientists suspect that RNA, a cousin of DNA, was the first molecule to bridge this gap. Unlike DNA, which is stable but inert, RNA can both store genetic information and catalyze chemical reactions. In what is called the RNA world hypothesis, early life may have been built from strands of RNA that copied themselves imperfectly, introducing variation. Natural selection, even at this molecular scale, would favor sequences that replicated better, catalyzed more reactions, built crude membranes. Slowly, chemistry became biology. Slowly, molecules learned to persist. Others suggest life began not in shallow pools, but in the deep, dark oceans at hydrothermal vents where minerals and heat created chemical gradients. At such vents, on Earth today, entire ecosystems thrive without sunlight, powered by the energy of chemical reactions. Alkaline vents, with their porous mineral structures, provide natural compartments where molecules can concentrate, interact, and perhaps self-organize. Here, the first metabolic cycles may have begun, fueled by the rich chemistry of Earth's interior. If true, then life is not fragile but robust, capable of beginning even in the crushing depths of alien seas, such as those on Europa or Enceladus. Each hypothesis, soup or vent, surface or depth, carries its own plausibility, and each expands the range of worlds where life might arise. There are other ideas still. Some suggest life may have begun with simple metabolic networks, cycles of reactions that stabilized and grew more complex before replication appeared. Others entertain panspermia, the possibility that life or its building blocks arrived from elsewhere, carried on comets or meteorites. Indeed, meteorites that fall to Earth today have been found to contain amino acids, sugars, even nucleobases, the raw materials of biology delivered from the heavens. If such materials rain down universally, then every world with oceans becomes a potential cradle. Life in this view may not be a local accident, but a cosmic inevitability, seeded wherever conditions are ripe. What unites these hypotheses is a profound realization. Life does not require miracles, only chemistry. Given energy, complexity, and time, molecules will explore possibilities. Most combinations fail, but some succeed, and those that succeed persist. On Earth, once the first self-replicating systems emerged, evolution took over. Over billions of years, it shaped the teeming diversity we know today. If life began so quickly on Earth, within a geological blink after conditions stabilized, then perhaps it begins easily elsewhere too. Perhaps the universe is littered not only with the ingredients of life, but with life itself. This perspective reshapes the way astronomers interpret distant planets. When they see a rocky world in a habitable zone, they do not see mere rock and gas. They see potential laboratories where chemistry might have already played out the great experiment. When they detect oxygen, methane, water vapor, they see echoes of the processes that transformed Earth's skies when microbes first exhaled. When they consider oceans beneath ice, they recall Earth's own vents and the resilience of life in extremes, in boiling springs, in Antarctic ice, in the radioactive ruins of Chernobyl. Life on Earth is not delicate but tenacious, thriving in acid, in salt, in vacuum, in crushing pressure. If such diversity exists here, why not elsewhere? And yet the mystery remains unsolved. We do not yet know the precise path from chemistry to biology. Each hypothesis is plausible, none yet proven. But even in this uncertainty lies strength. Life may arise through multiple routes, under multiple conditions. If so, then the probability of life in the universe multiplies. Our planet's story is not a singular blueprint, but one example among countless variations. This realization also tempers our search. When we look at the 98% planet, we must be cautious not to assume its life mirrors ours. Its biochemistry may be different, its molecules unfamiliar, its pathways alien. We may detect oxygen and methane, but the organisms behind them may be nothing like Earth's microbes. They may operate on cycles we have not yet imagined, leave biosignatures we do not yet recognize. To confirm life, we must expand our definitions and train ourselves to expect the unexpected. For in all likelihood, the cosmos harbors forms of life stranger than any we have yet conceived. Still, the lesson of Earth endures. Life does not hide in perfection. It begins in chaos, thrives in extremes, adapts endlessly. It is not a miracle, but a consequence, a pattern written into the fabric of chemistry itself. And if that is true here, then it is true everywhere. On worlds of rock and ice, beneath alien suns, in oceans we will never swim, life may already be unfolding, its molecules whispering across the void, waiting for us to recognize them.
Astrobiology stands today on the edge of a new epoch. For centuries, the discipline was speculative, a mixture of philosophy, astronomy, and biology, stitched together by questions rather than answers. But the discovery of a planet with a 98% likelihood of life has crystallized the field into something sharper, more urgent. No longer is the question, is life out there, merely abstract? It is practical, experimental, testable. And to meet it, humanity is designing tools unlike any we have ever built, instruments and missions conceived with a single purpose: to transform probability into proof. The James Webb Space Telescope has already shown us the power of looking into alien skies, teasing out the signatures of molecules from the faintest glimmers of light.
But Webb is only the vanguard. On drawing boards across the world are concepts for telescopes so ambitious they border on the fantastic. LUVIR, the Large Ultraviolet Optical Infrared Surveyor, is envisioned as a space observatory with a mirror as large as a city block, capable of directly imaging Earth-sized exoplanets around sun-like stars. With such a telescope, astronomers could measure seasonal changes in an alien atmosphere, track cloud systems, perhaps even detect the red edge of vegetation, a spectral fingerprint that plants on Earth produce as they reflect near-infrared light. HABEX, the Habitable Exoplanet Observatory, would pursue similar goals, but with a more specialized focus, pairing a space telescope with a starshade, a vast flower-like disk flying tens of thousands of kilometers away to block out the host star's glare. With such instruments, planets that today are whispers of data could become worlds, revealed in color and detail. Ground-based giants are rising too. The extremely large telescope in Chile, its segmented mirror merely 40 meters wide, will have the power to study exoplanet atmospheres from Earth. Alongside it, the giant Magellan telescope and the 30-meter telescope will form a trinity of unprecedented capability. Adaptive optics, systems that bend mirrors thousands of times per second to cancel out atmospheric distortion, will sharpen their gaze until they rival space observatories. These terrestrial behemoths will not only measure gases, but may even glimpse glints of oceans, subtle reflections of starlight off alien seas. They are the tools that will bridge the gap between probability and direct observation. But telescopes alone are not enough. To confirm life requires missions tailored not only to detect atmospheres, but to identify biosignatures unambiguously. Biosignatures are the fingerprints of life. Oxygen-methane disequilibria, nitrous oxide, chlorophyll-like pigments, even the spectral pattern of complex organic molecules. Yet each must be weighed against abiotic processes, natural mechanisms that could mimic them. The future of astrobiology lies in discriminating between false positives and true signals. Instruments are being designed to scan across multiple wavelengths, to detect not one molecule, but entire suites, to analyze ratios and patterns that together reveal the unmistakable hand of biology. New fields are emerging as well. The study of technosignatures, evidence of technology rather than biology, is increasingly entwined with astrobiology. Telescopes may soon search not just for natural gases, but for pollutants like chlorofluorocarbons, compounds that do not occur without industry. Infrared surveys may seek the waste heat of advanced civilizations. Even anomalies in starlight curves might suggest megastructures orbiting stars. What was once speculative science fiction is becoming a matter of instrumentation and algorithms. If biology can leave signatures in a spectrum, so too can intelligence. And then there is the dream of probes. For now, the stars are too far. A journey to the nearest exoplanet would take tens of thousands of years with present rockets. But bold concepts are being tested. Breakthrough Starshot, for instance, imagines gram-sized probes driven by immense ground-based lasers sailing on light at a fraction of the speed of light. In decades, rather than millennia, such craft could cross the interstellar gulf, carrying cameras and sensors no larger than a chip. If they succeed, they may one day send back images of alien oceans, alien continents, alien skies. It is a technology still in its infancy, but the discovery of life-bearing worlds has breathed new urgency into its pursuit. Closer to home, astrobiology turns to analog worlds in our own solar system as laboratories of possibility. Missions to Mars, Europa, Enceladus, and Titan are designed not only to search for life locally, but to refine the methods we might one day apply to exoplanets. On Europa, NASA's Clipper will sample plumes and measure chemistry. On Titan, the Dragonfly rotorcraft will hop across dunes and lakes, testing exotic organics. Each mission teaches us how to detect life in conditions far different from Earth, expanding the catalog of biosignatures we might recognize in distant spectra. They are testbeds, rehearsals for the grand performance of interstellar astrobiology. Meanwhile, on Earth, the laboratory work continues. Scientists recreate ancient oceans in glass flasks, test how molecules assemble under heat, light, and pressure, simulate alien atmospheres under ultraviolet lamps. Genomics and synthetic biology probe the limits of life, creating organisms with artificial genetic codes, demonstrating that DNA and RNA are not the only possibilities. Extremophiles, microbes that thrive in acid, in salt, in radiation, in near-boiling water, are studied as models of how life might persist under alien extremes. Every experiment broadens our sense of the possible, teaching us that biology is not a narrow thread, but a vast tapestry of resilience. This expansion of astrobiology is not purely scientific, it is cultural, even civilizational. The knowledge that we may not be alone infuses urgency into funding decisions, inspires students to enter the sciences, drives international collaboration. Agencies that once worked in competition increasingly speak of shared missions, recognizing that the discovery of life will not belong to one nation, but to humanity. Private companies, too, see opportunity, envisioning telescopes, probes, even starships built with the agility of industry. Astrobiology is no longer the fringe, but the frontier, a discipline that unites physics, chemistry, biology, engineering, philosophy, and art under one banner: the search for life. But with this ambition comes responsibility. The moment we confirm life elsewhere, whether microbial or intelligent, humanity's perspective will shift forever. We must be ready not only to detect, but to interpret, to respond, to integrate. What we find may challenge our assumptions, demand humility, force us to rethink the very definition of life. It may show us that biology is inevitable, or that it is fragile and rare. Either way, the consequences will be profound. For now, we stand at the threshold. Telescopes are being built, probes are being designed, missions are being planned. The tools of the next decades will be sharper, broader, deeper than anything we have yet wielded. The discovery of a world with a 98% chance of life has ignited this momentum, turning distant dreams into engineering requirements, transforming philosophy into blueprints. In laboratories and control rooms, the future is being assembled piece by piece, mirror by mirror, sensor by sensor. Soon, the cosmos will reveal itself not in probabilities, but in realities. Soon, we will look not at hints and whispers, but at proof.
The discovery of a planet with a 98% chance of life does not simply confront us with scientific data, it confronts us with ourselves. It forces us to ask questions that have lingered in philosophy for millennia, but which now arrive with a weight of immediacy. If we are not alone, what does it mean to be human? If life is common in the universe, then our story is not singular, but one thread in a vast cosmic fabric. That realization can be humbling, frightening, exhilarating, and destabilizing all at once. From the earliest myths, humanity has sought to understand its place in the cosmos. Ancient cultures traced the motions of stars to divine stories, projecting gods into the heavens, building meaning into patterns. The Copernican revolution shattered the belief that Earth was the fixed center of creation. Darwin's theory of evolution revealed that humanity arose from the same processes that shaped all creatures. Each of these revelations moved us outward, step by step, from a universe built around us to a universe in which we are participants. The confirmation of life beyond Earth would be the next great turning, the moment we step across the boundary of anthropocentrism once and for all. No longer would we be the solitary miracle, we would be part of a continuum that stretches from our planet to the stars.
For some, this prospect will be deeply unsettling. Religions and philosophies built upon human uniqueness may struggle to absorb the shift. Yet others may find affirmation in the idea that creation is more abundant than imagined, that life flourishes not just here, but across the cosmos. Theologies may adapt, as they have before, to a universe larger than previously conceived. Ethical frameworks may expand, recognizing that our moral circle might one day encompass beings not of Earth. Philosophers debate already: should we prepare a new branch of ethics, an astroethics, to guide our behavior toward alien life? What obligations will we hold if we discover microbes on Mars or intelligent species on distant planets? Will we protect them as we protect endangered ecosystems on Earth? Or will curiosity and ambition push us toward exploitation? The cultural impact will be immense. Literature, film, and art have long imagined contact with the other, weaving visions of utopia and dystopia alike. Science fiction has served as a rehearsal, a cultural imagination that explores the possibilities before they arrive. But when the probabilities collapse into certainty, the stories will no longer be fiction. Humanity will find itself at the threshold of a new narrative, one in which we are characters not of isolation, but of communion. Children will grow up knowing that life exists elsewhere. Their imaginations will stretch outward in ways that ours could not. Civilizations that define themselves by boundaries, national, religious, ideological, may find those boundaries blurred against the scale of the cosmic. We may, for the first time, be compelled to see ourselves as one species, one planet, in a universe alive. Yet the discovery will not only reshape our sense of identity, it will also shape our future actions. If life thrives elsewhere, then Earth is not an island, but a participant in a network of biospheres. That realization could instill a sense of stewardship. Our planet becomes not just our home, but our contribution to a living cosmos. To destroy it through negligence, through climate change, ecological collapse, nuclear war, would not only be a loss to us, but a diminishment of the universe itself. Conversely, the knowledge that life is abundant may push some toward recklessness, undercutting the sense of fragility that drives protection. Why worry if life sprouts everywhere? But such thinking ignores the uniqueness of Earth's biosphere, its billions of years of history, its cultural richness, its particular form of beauty. Even if life is widespread, this life, here, is irreplaceable. There is also the question of communication. If the 98% likelihood becomes certainty not of microbes but of intelligence, the ethical and philosophical stakes escalate dramatically. How should we reach out? Should we? The search for extraterrestrial intelligence, SETI, has long listened for signals, but debates continue over messaging extraterrestrial intelligence, whether actively sending our own messages is wise. Some argue that communication is an ethical imperative. If we know others exist, silence would be arrogance. Others warn that advertising our presence could expose us to unknown dangers, that survival requires caution. The discovery of intelligent life will force humanity to resolve these debates not as speculation but as policy. The future may hinge on choices made in radio telescopes, in data streams, in encoded beacons launched into the dark. For individuals, the discovery may prompt existential reflection. How do our lives matter in a universe where we are not alone? For some, the answer may be despair. If we are one among countless civilizations, what weight has our existence? But for others, the opposite: connection, belonging, the sense that our story is woven into a vaster whole. The knowledge that consciousness has arisen in multiple places may deepen the mystery of existence, making it more wondrous, not less. Just as the sight of galaxies does not diminish the beauty of stars, but multiplies it, so too might the realization of other lives multiply the meaning of our own. The arts will respond first, as they always have. Music, painting, poetry, film, they will strive to capture what words struggle to contain, the feeling of cosmic kinship. Nations will respond next, reshaping policies, perhaps forging treaties to govern contact. Science will accelerate, driven by the need to understand not just biology, but communication, psychology, culture beyond Earth. Education will shift, teaching children not we are alone, but we are connected. Even economics may change as humanity contemplates technologies and resources not yet dreamed of, exchanges that could span light years. And beneath it all, the philosophical question persists. What does it mean to be alive in a universe of life? Perhaps the answer lies not in isolation, but in dialogue. Life elsewhere will not erase our individuality, it will illuminate it. Just as meeting another person teaches us something about ourselves, so too will meeting another world. Their biology will reflect possibilities we never imagined. Their cultures, if they exist, will mirror and challenge our own. In their presence, we will better understand what it means to be human. Yet we must also prepare for uncertainty. What if the 98% life-bearing planet reveals nothing but barren oceans, lifeless despite promise? What if we find life, but it is microbial, silent, indifferent? The disappointment may be as profound as the discovery would have been. But even then, the philosophical consequences remain. Life is possible elsewhere, and if it happened once beyond Earth, it can happen again. The cosmos will remain a place of potential, a stage set for endless stories.
As telescopes refine their gaze and missions are launched, humanity moves toward these questions not as speculation, but as destiny. The planet that whispers of life is a mirror held up to our species. In its reflection, we see possibility, fragility, and choice. The discovery will not tell us what to become, it will only remind us that we are part of something larger, and the meaning we draw will depend on the paths we choose.
The fate of Earth is no longer a question confined to the boundaries of our own planet. When astronomers point to a world with a 98% probability of life, they are not merely cataloging an exoplanet. They are holding up a mirror in which Earth's destiny reflects back at us. For billions of years, this world has nurtured life, producing coral reefs, rainforests, whales, and humans capable of contemplating the stars. Yet never before has our species faced the stark realization that survival is not guaranteed, that our decisions in the coming centuries will determine whether Earth remains a flourishing oasis or becomes a cautionary tale written into the silent records of geology. The discovery of another life-bearing world sharpens this truth. It tells us that while life may exist elsewhere, our responsibility for our own biosphere is absolute. No alien civilization will arrive in time to save us from ourselves. If we wish to endure, we must choose preservation, not destruction. Climate change is perhaps the most urgent front in this battle. The same tools that allow us to detect the signatures of alien atmospheres, spectroscopy of gases like carbon dioxide and methane, also illuminate the changes in our own sky. Satellites orbiting Earth read the chemistry of our atmosphere with precision, revealing the steady rise of greenhouse gases, the thinning of ice caps, the shifting of weather patterns. To search for other worlds is to hold Earth under the same scrutiny, to realize that our planet's signature, if seen from light years away, would already bear the mark of industrial activity. Astronomers call this the technosignature, a planet's evidence of intelligent modification. From afar, Earth would appear as a world in crisis, a civilization altering its climate faster than ecosystems can adapt. To know that others may be watching us, perhaps even judging whether we survive, should awaken in us a new sense of urgency. For if we collapse under the weight of our own excesses, the universe will not mourn, it will simply move on, while we vanish into obscurity. Yet within the darkness of risk lies the brilliance of possibility. The technologies we are forging to study exoplanets, to explore Mars, to harvest clean energy are the same technologies that can transform our relationship with Earth. Solar panels that harvest starlight echo the instruments that search for habitable zones. Fusion research, driven by the dream of endless energy, reflects the fires that power the stars themselves. Artificial intelligence sorts through torrents of data from telescopes, just as it can optimize our use of resources at home. The pursuit of other worlds feeds the preservation of this one. In learning to see across light years, we gain the perspective to act wisely across generations. The discovery of another life-bearing world sharpens this truth. It tells us that while life may exist elsewhere, our responsibility for our own biosphere is absolute. No alien civilization will arrive in time to save us from ourselves. If we wish to endure, we must choose preservation, not destruction. The discovery of a planet likely teeming with life also challenges us to reconsider the trajectory of human civilization. Expansion into space has long been envisioned as our destiny, an escape from the limits of Earth. But the reality is that no other planet will be as forgiving, as abundant, as suited to us as this one. Even if we reach distant worlds, we will arrive as strangers, fragile, and dependent on technology. Earth remains our anchor, the nursery from which we emerge. To neglect it while chasing the stars would be a profound mistake. The lesson of the 98% planet is not escape, but responsibility. If life elsewhere is precious, then life here is sacred. Still, the dream of reaching other stars persists, and rightly so. For humanity is a species of wanderers, and the pull of the horizon is written into our nature. The knowledge that another world harbors life will fuel efforts to develop interstellar travel, to find ways to bridge the abyss of light years. Concepts once confined to theoretical physics, warp drives, solar sails, generation ships, will find new urgency. Our children may grow up believing not only that the stars are inhabited, but that one day contact is possible. Whether that future lies centuries or millennia away, its seed is planted now. And with that seed comes a profound question. What kind of civilization will we be when we arrive? Will we be emissaries of cooperation, bringing knowledge and respect? Or will we repeat the mistakes of colonialism, exploiting new worlds as we have exploited our own? The fate of Earth and the fate of our character are inseparable. If we cannot preserve the balance of our own biosphere, how can we claim to deserve a place among the stars? If we cannot resolve conflicts here without war, how can we hope to greet another civilization with peace? The 98% planet becomes not just a scientific milestone, but a moral compass. It asks us to grow, to mature, to rise above the divisions that threaten to tear us apart. The cosmos is vast and perhaps patient, but the window of survival is not infinite. Our choices today echo into the future, shaping whether humanity will be remembered as a fleeting experiment or as a lasting participant in the story of the universe. This realization infuses even the smallest actions with weight. A forest protected, a technology invented, an ecosystem restored. These are not isolated victories, but part of a continuum that stretches outward to the stars. Each decision in favor of sustainability affirms our place in the cosmos. Each step toward peace strengthens our readiness for the challenges that lie ahead. The discovery of another world with life is not an excuse to abandon Earth. It is a call to cherish it more deeply than ever before. For we now know that we are not the only living story, but this story is ours to write. And as humanity contemplates its future, the perspective of cosmic time reminds us of humility. Planets rise and fall, stars are born and die, galaxies collide and merge. Against that backdrop, the span of human history is a flicker, and the span of a human life a spark within it. Yet meaning does not vanish in immensity, it intensifies. For it is precisely because we are fleeting that our choices matter. To live wisely, to protect life, to reach outward with curiosity and compassion, that is how we leave a mark that endures beyond the brevity of our years. The 98% planet does not diminish Earth's importance. It magnifies it, reminding us that in a universe alive, our responsibility is not less, but greater.
The story of a planet with a 98% chance of life is not simply about astronomy, nor is it merely about the search for others in the cosmos. It is, at its heart, about us, about who we are and who we choose to become in the face of vastness. For when we lift our eyes to the night sky and imagine creatures walking beneath alien suns, we are not only searching for them, we are searching for ourselves, reflected in the possibilities of life beyond Earth. Every telescope trained outward is also a mirror turned inward, reminding us that the first and greatest test of our ability to recognize life lies here, at home. Imagine Earth as if it were distant, glimpsed through the lens of an alien observatory. They would see a small blue dot circling an unremarkable yellow star, wrapped in an atmosphere rich in oxygen and carbon dioxide. They would see oceans glittering, clouds swirling, polar ice reflecting sunlight into space. They would notice signatures of methane, chlorophyll, and strange fluctuations in gases that suggest industrial activity. They would conclude, as we have concluded of the 98% world, that this planet almost certainly hosts life. And if their minds were anything like ours, they would wonder, is that life intelligent? Does it know of us? Does it cherish what it has? Or does it squander it? Do they dream of the stars as we do? In their gaze, we become the mystery, and Earth the exoplanet. Suddenly, we realize that we are already the proof that life exists elsewhere, for to them, we are the 98% planet. This shift of perspective is the greatest gift astronomy can give. It shows us that we are not apart from the cosmos, but inseparably part of it. The elements in our bones were forged in stars. The water in our blood once drifted as interstellar ice. The carbon in our breath was woven in ancient suns. We are the universe made aware, the cosmos learning to see itself. To search for life is not a pastime. It is the natural unfolding of self-awareness on a cosmic scale. And the discovery of another life-bearing world is the culmination of that search, the moment when the universe answers back, yes, you are not alone. Life is not an accident. It is a pattern written into the fabric of existence. But with that answer comes responsibility, heavier than we have known. For if life is common, then its preservation is sacred. If civilizations can rise, then they can fall. The silence of the stars, the absence of radio beacons or interstellar emissaries warns us that survival is not inevitable. Perhaps many worlds like ours have flourished, only to wither. Perhaps countless civilizations have reached the precipice we now face and did not cross it. The Fermi paradox, the question of why the galaxy is not teeming with visible life, may find its answer in our own choices. If we fail, we will become one more lost voice in that silence. If we endure, we will prove that the silence can be broken. Endurance will not come easily. It demands unity, the transcendence of divisions that seem immovable,
the recognition that borders and nations are illusions compared to the shared destiny of humanity. It demands wisdom, the ability to balance progress with restraint, to wield technology not as a weapon, but as a tool for life. It demands imagination, the courage to dream of futures beyond our present limits, to chart courses across oceans of space without fear. These qualities are not yet secure. They must be cultivated, nurtured, chosen. But the possibility lies within us, just as it lay within the first cells that divided, the first fish that crawled onto land, the first humans who lit fires and looked to the sky. And so we stand at a threshold. Behind us lies a history of struggle and triumph, of art and war, of discoveries that reshaped our place in the cosmos. Before us lies a future that could end in silence or blossom into continuity. The 98% planet is more than a destination. It is a reminder that life is precious, that Earth is irreplaceable, that we are not isolated wanderers in a dead universe, but members of a larger, unfolding story. When our descendants finally set foot on alien soil, when they look into the eyes of life born under another sun, they will not just be explorers, they will be ambassadors of Earth. What message will they carry? What legacy will they bring? That is the question we must answer now, while the choice is still ours. The universe does not hurry. Stars burn for billions of years, galaxies drift in slow collision, black holes wait in silence. But we are brief. We are fragile. And it is precisely because of our brevity that our choices are powerful. We can waste our gift in division, or we can rise together to meet the cosmos. The 98% planet shows us that we are not alone in possibility. The rest is up to us, to choose life, to choose survival, to choose to be not the last, but the first, pioneers of a future in which Earth is remembered not as a world that failed, but as the cradle of a civilization that learned to endure, to explore, and to join the chorus of life that sings among the stars. And as the lights of our cities glow faintly against the night sky, and telescopes gather the photons that have crossed light years to whisper their secrets, one truth becomes clear. The universe has spoken. Life is not confined to Earth. The question is no longer whether we are alone. The question is this: will we, fragile and fleeting, rise to deserve the company of the stars?